What governs the motion of objects around us? To move a football, you kick it. But what happens once it's already moving? What keeps it going, and why does it eventually stop? For over 2 millennia, the definitive answer came from the Greek thinker Aristotle. He argued that an external force is always required to keep a body in motion. He observed that an arrow shot from a bow keeps flying because the air rushing in behind it continually pushes it forward. It is easy to see why this explanation survived for so long. It matches our daily human experience. If a child pushes a toy car across the floor, they have to maintain their grip and keep pulling to keep it moving. As soon as they let go, the car rolls to a halt. But Aristotle missed a crucial invisible variable. The moving toy car doesn't stop because it runs out of a pushing force. It stops because an external force, the friction between the wheels and the floor, actively opposes its motion. To find the true laws of nature, we have to look past the practical constraints of our friction-filled reality. We have to imagine a world where uniform motion is completely unopposed. In the 17th century, Galileo approached this problem by isolating the variables. He studied how objects behaved on inclined planes where friction was minimized. This chart shows the first basic state. Objects rolling down an inclined plane accelerate. Gravity pulls them, so their velocity increases. Conversely, objects rolling up an inclined plane retard or slow down. They are moving against gravity, so their velocity drops. Galileo deduced that motion on a perfectly horizontal plane is the exact intermediate between these two states. With no downward slope to cause acceleration and no upward slope to cause retardation, an object rolls at a constant, unchanging speed. A state of rest and a state of uniform linear motion are physically equivalent. In both scenarios, there is zero net force acting on the body. To test this logic, Galileo devised another thought experiment, this time using a double inclined plane. If you release a ball from rest on one slope, it rolls down, builds speed, and climbs the opposite slope. Assuming the ramps are perfectly smooth, the ball reaches the exact same height it started from. If the angle of the second slope is decreased, the ball still possesses the momentum to reach that original starting height, but because the incline is shallower, it travels a much longer distance to get there. Now push this logic to its limit. If the second slope is lowered until it is perfectly horizontal, the ball continually travels forward, seeking a height that the flat plane will never allow it to reach. In this idealized situation, the motion never ceases. The ball rolls for an infinite distance. This extrapolation proved Aristotle was wrong. An external force is not needed to keep a body moving. Force is only needed to alter how a body is already moving. This inherent property of matter is called inertia. It translates to a literal resistance to change. A body will not alter its current state unless compelled to do so. If the net external force is zero, a body at rest stays at rest, and a moving body continues with a uniform velocity. Isaac Newton recognized the brilliance of this deduction. He took Galileo's concept of inertia and formalized it as his first law of motion. You can see this law in its purest form far away from the friction of Earth. An astronaut drifting in deep space, with no rockets firing and no gravitational pull nearby, experiences zero net external force. Without anything to stop them, they glide forward at that exact speed indefinitely. By isolating the variables of motion on simple wooden slopes, Galileo mentally stripped away the interference of friction. This logic uncovered the laws of momentum and established the foundation for all modern mechanics.